Good morning, everyone. My name is Max. I'm a master's student working with Pierre at UTM, and my presentation for today is called Evolving Artificial Neural Networks to Imitate Human Behavior in Shinobi 3, Return of the Ninja Master. Let's get started. Alright, so first things first, evolving. What does that even mean? Well, by evolving, I mean making use of computational techniques that draw inspiration from concepts in biological evolution and natural selection in order to solve various problems. These techniques are called evolutionary algorithms. So what do these algorithms look like? Well, since they've been around for much longer than I've been alive, I'll let you guess that they now come in just about every shape and size. However, certain concepts can be found across most of its variants. First, one of the landmark concepts, populations. A population, in the context of an evolutionary algorithm, is a group of artificial agents who, throughout the algorithmic process, repeatedly go through successive stages. What are those stages? Well, in most cases, there are three of them, commonly referred to as variation, evaluation, and selection. These stages form a cycle that repeats indefinitely. So let's go through each one. First up, variation. This is the stage during which the artificial agent's inner mechanism are modified. In just about every case, these changes are, within some preset boundaries, completely random, which is why they are often called mutations. Next up, evaluation. This is the stage during which artificial agents are tested. What these agents are tested on, as long as it's possible to attach a quantitative label to the performance, can be pretty much anything. The test score obtained by each agent is often referred to as their fitness. The final stage is selection. This is where it is decided, based on the previously computed scores, which agents we would like to continue working with. Alright, so now that we have a high-level understanding of these stages, let's illustrate them with a high-level example. So here's our initial population, composed of 4 agents, and let's say that we want these agents to get really good at playing our favorite video game here at Neuroevolution Shinobi 3 Return of the Ninja Master. Alright, so let's go back and let's say that in our later example, agents are created as exact duplicates of each other. And so, everyone looks the same. To kick things off, agent first enter variation. Now, to remain quite abstract, let's go ahead and say that the random mutations in the agent's inner mechanism are reflected by slight changes in their appearance, resulting in each of our agents now looking a little different from one another. Alright, so now it's time for evaluation. So one of the most important parts of working with evolutionary algorithms is to find a good quantitative metric, aka fitness function, that matches our qualitative objectives. So, what's a good quantitative metric for playing Shinobi? Well, just in like most video games, there's a pretty good one right in front of our eyes, and that is the in-game score. So one example of what we could do to evaluate these agents is to simply give them 10 seconds to get as many points as possible. Alright, so let's say we did just that for all of our agents and that all got different scores. We're now ready for selection. So, some agents look more promising than others, and we like to give those more chances to further show their potential. Now, although evolutionary algorithms are well known for things like breeding agents together to produce new interesting agents, this operation isn't always very straightforward to put into practice. So for now, let's keep it at one of the most basic selection operations, which is to simply hold on to the top 50% agents and duplicate them. And that's it. This constitutes one full circle of our algorithmic process. Now, in practice, one iteration is of course not enough to get to our desired outcome. And so, right after this selection stage, we go right back for a new variation round. Alright, so now that you know about evolutionary algorithms in a general sense, let's talk about their application to artificial neural networks, aka neuroevolution. So, just in case, for those that don't know, artificial neural networks are those computational techniques that have become immensely popular in the past few years that sort of try to replicate the way the brain works with its neurons and connections. Alright, so we were previously talking about the agents having some inner mechanism that can change during the variation stage. Well, artificial neural networks are one potential class of inner mechanisms. And so, going back on our evolutionary algorithm process, we can now imagine that our agents now all have the same little neural network inside of them. Alright, so now we're finally able to give a more explicit example for what to do during the variation stage. one potential mutation that we can apply to all of our agents is to give a little tweak to one of the many network's connections. And so once this is done, we get to carry on with evaluation and selection in the exact same way that we were doing for regular evolutionary algorithms. No changes there. Alright, so that concludes our mini tutorial. Now, before we move on, let's ask a difficult question. Why bother with evolutionary algorithms? Didn't they kind of die off like 20 years ago? Well, that's a good question, because for those that might not know, in recent times, evolutionary algorithms have not been that impressive, and that has echoed into the fact that they currently have close to no real-world application. For most tasks, other algorithms are currently simply better suited. So why bother? Well, I'll give you two reasons. The first one is computational resources are becoming increasingly powerful and show no signs of stopping. How has that affected artificial intelligence? Well, techniques that have been able to leverage this ever-increasing amount of computation have inevitably rushed past the others in terms of how capable they can get. And that's where Neuroevolution comes in. Out of all the present techniques, these algorithms are at the very top in terms of scaling potential to massive compute, higher even than modern deep learning. So why haven't we heard about them? Well, as I will show later, in order to start taking off, these algorithms need a non-negligible amount of resources, which not everybody can get their hands on at this current moment. Now, the second reason is, due to the flexibility of the evolutionary algorithm framework, neuroevolution is very flexible and allows for incredibly malleable artificial neural networks. This is very important to us as CNeuromod, because in order to account for all the brain data and all the stimuli, the videos, the images, the sound, the language, and others, we are going to need very flexible networks. Alright, so are there any signs of life for this discipline out there right now? Have people done anything with this that could give us a little direction and reassure us that this is not all talk no show? There is indeed. A few years ago, researchers at Uber AI Labs, now working at OpenAI, found that applying those very simple evolutionary algorithms to modern deep neural networks, while making use of large computational resources, was sufficient to beat many state-of-the-art techniques on modern video game benchmarks. Alright? And so if you're around for last year's CNeuromod Day, you'll remember that we applied this very idea to Shinobi and got agents that were really good at the game. As you can see, this agent mostly uses projectiles to eliminate enemies. Alright, so that's cool, but here at CNeuromod, we're not actually interested in getting artificial agents that are good at video games. Actually, quite the opposite, we're trying to get agents that behave like humans, even if that means making mistakes. Can we do that with Neuroevolution? Well, since there wasn't any clear existing Neuroevolution specific method, we looked in the deep learning camp at one of the most impressive modern techniques, generative adversarial networks, aka GANs. Now, if you've been keeping an eye on modern AI work, you'll probably know that it is now possible to generate faces of people that look, without exaggeration, indistinguishable from actual people. Now, before I give an overview of how this technique works, let me motivate the need for it. So when it comes to getting high scores in a video game, or finding whether an image is of a cat or a dog, it's pretty easy to tell whether agents are doing good or not. But how can we tell how good an agent is at generating faces, or in our case, playing Shinobi like a human? Well, it's not obvious at all. We have some qualitative goals, but we don't really know how to turn them into good quantitative objectives. We cannot say things like, oh, wow, that looks 70% similar to how a human face looks like. Or wow, that's 80% similar to how a human plays Shinobi. So here's the genius behind this idea. Instead of trying to find a way to tell the agent how good he's doing, let's bring in another agent to decide that for us. This new agent is called a discriminator. It looks at real data, in this example, images of digits, and data created by our original generator agent. And its task is to tell which is real and which is fake. Now, I won't get into the precise details of how these networks are trained, but what I can tell you is that through this process, the discriminator gets increasingly good at telling the difference between the two sources of data. And so in order to counter that, the generator gets increasingly good at fooling the discriminator by getting better at making fake images that look real. Super simple concept. So how do we transfer that to evolutionary algorithms? Well, let me introduce evolutionary adversarial generation. Now, remember, in evolutionary algorithms, we work with populations. So instead of one generator and one discriminator, we need a population of generators and an equal sized population of discriminators. We randomly match generators and discriminators, and when it comes to data, we attribute one piece of real data to each discriminator. Alright, so this is kind of abstract. What does it look like in Shinobi? Well, here it goes. In that scenario, our generators are bots playing the game, our dataset is composed of the games played by our subjects, and we have our discriminators in between looking at both. Alright, so let's delve a little deeper into what happens within each of these matches. So here's one match. We have one player agent, one discriminator agent, and the video of the subject's play. The first thing that happens is the player agent plays a game which produces its own video, and now the discriminator, which of course doesn't know which is which, can start getting busy. It watches the generated video and gives out its confidence that the video it just watched was the subject's. As this was not, its fitness is reduced by this confidence, while the player agent's fitness is increased by the inverse amount, since the greater the confidence, the better it fooled the discriminator. Now, the discriminator looks at the subject's video, and same thing gives out a confidence that this is the subject's video. But it is now rewarded for this confidence. And that's it for evaluation. So this little process right here is repeated for each pair of agents, and once this is done, and all agents have obtained their fitnesses, we can move on to selection. Now that we have two populations, we can simply select over each population independently, holding on to and duplicating the top 50% in each. And that's the whole process. Alright, so last year we got to this point. We made use of this evolutionary adversarial generation technique, combined it with deep neural networks, and here's what we got. So here's how the human player, Sub-01, plays. Lots of jumping and kicking, but no projectiles. And that was our agent. Lots of jumping and kicking, barely any projectiles. Alright, so maybe some similarity, but nothing to write home about. And so last year, at the end of the presentation, we proposed to carry on with three directions. New, more flexible neural networks, better adapted for evolutionary algorithms, more diverse subject data, and better utilization of compute. So let's look at what progress we made on these 3 points, starting with the first. Evolving more flexible neural networks. Introducing neural networks of dynamic complexity. Before we begin, a little bit of backstory. Nowadays, in terms of evolving dynamic networks, the most revered reference comes to us from an algorithm named NEAT, developed in the early 2000s. In this algorithm, mutations modify the structure of the neural network. As you can see here, the first structural mutation is to add a connection between two nodes. The second mutation splits a connection in half in order to add a node in between. And the third important operation is to breed networks together in order to create new ones. So this idea is super cool, but it has 3 big issues. First, it doesn't work on image data. Second, in order to work properly, it has dozens and dozens of parameters that need precise tuning. And finally, because of its design, it cannot scale well to big compute. So, conclusion, very interesting point of entry, very nice simple ideas, too many issues for our purposes. Alright, so a little more about our first issue, the fact that this NEAT algorithm cannot handle image data. Well, that sort of makes sense. This algorithm was developed in the early 2000s, and at the time the amount of image and video data was not nearly as colossal as it is today. Modern deep neural networks, on the other hand, do have a way to handle this data. All you need to know for now is that in order to do so, they make use of 2 operations called convolution and pooling. These 2 operations are used at the front of these modern networks, while the type of operations that NEAT was trying to perform dynamically, linear transformations, are at the back. And so, due to how prevalent these 2 sections are in modern deep neural networks, we thought we'd start off by creating networks that kept that structure in place, while completely getting rid of parameters to be tuned and designs that made it impossible to scale to large compute. So here's what we got. A first dynamic network module in which nodes perform both convolution and pooling operations, and a second module which performs linear transformations. In both cases, nodes of course apply a nonlinear activation function at the end of their computation. This first dynamic image processing module has the structure of a tree. It can grow branches of nodes, prune these branches, make the branches thicker, but also contract them. The other module, very similar to needs, can grow connections between nodes, prune these connections, grow some new neurons, but also delete them. And these two modules can easily be combined. Since the first, image processing module, is a tree, it creates leaves from its branches, and when a new leaf is created, the second module reacts by creating a neuron to handle it. Similarly, when a branch is deleted, the leaves resulting from that branch are two, and so the second module gets rid of the corresponding neurons. And that's about it. All these mutations are set to have the same probability of occurring, and no special parameter needs to be adjusted at any time. Alright, so back to our old future direction slide. What progress did we make in leveraging increasing amounts of compute? Well, the biggest work we've done was to further look into the properties of computer clusters in order to draw additional benefits. So in order to get into that, let me explain a few things first. In every computer, there is something called a processor, which you can think of as the brain of the computer. And within these processors, there are many cores. In most cases, for each core, you can have one process running, and so with 4 cores, you can have 4 processes running at the same time. In a normal computer, there is most often one processor with 4 or maybe 8 cores, and so you can do 4 or 8 things at once. In a supercomputer, however, there are dozens and dozens of cores. So why does this matter to us? To explain why, let's come back to our evolutionary algorithm. Remember the 3 stages? Well, they have some interesting properties. First, for the variation stage, you do not need to know how mutating the first agent turned out before mutating the second one. If you have the resources, you can perform variation on each of the agents independently. In technical terms, this operation is embarrassingly parallel. Next, for the evaluation stage, it's the same thing. You don't need to know how well the first agent performed in order to test the second. You can evaluate them all at once. Once again, embarrassingly parallel. Finally, for selection, we need to compare all fitnesses together, so we cannot distribute this workload as easily. However, comparing fitnesses is a very cheap operation, so it's not a problem at all. So coming back to our computers, for the normal computer, if we have 4 cores, we can work on 4 agents at once. But if we have dozens and dozens of cores, we can work on dozens and dozens of agents at once. Why is this important? Well, the more agents we can variate and evaluate at the same time, the more we can try different variants and explore potentially good directions. Alright, so here's how we run evolutionary algorithms in parallel. For this example, let's say we have 6 cores, and so 6 processes that can run at the same time on the computer. Each process gets 1 agent, performs a variation, and evaluates the agent. Alright, so we got 3 agents, and we want to keep and duplicate, and 3 that we want to discard. To do that, for each process that has in its possession a selected agent, we link a process that has a discarded agent. The earlier sends a copy of its agent to the latter, and now we're ready to repeat the process once again. Because sending data between cores on a supercomputer is very inexpensive, this technique scales really well to however many cores. Alright, so this is it for the technical stuff. Let's move on to the good stuff. So, before I get to our new experiments, let me remind you of how we acquired the data. Paul-Henri Mignot and Basile Pensard developed a training console that each participant brought home to play Shinobi. Every game they played was recorded in the console, and Yann Harel then ran some analysis to figure out when the subjects were steady in terms of their performance. Any data past that point was used in our experiments. So here we go with the experiments. At the time of this study, 2 subjects, Sub-01 and Sub-02, were deemed ready enough to run experiments on. We work with the new networks of dynamic complexity, but because of the new enhanced communication protocol just described, we also re-experiment with static deep neural networks. For each model-subject pair, we try 4 different population sizes, equal to the number of processes used. And we run each of these for 48 hours, with a checkpoint every 12 hours. In order to evaluate the quality of our results, we perform a qualitative analysis of each subject's behavior in the first 5 seconds of the game, and creates a color grading scheme to compare the agent's behavior with the subject's. And here are our results. As you'll notice, for each type of model, running the algorithm for longer doesn't produce the biggest change in quality. However, increasing the population size clearly does. So let's look at some videos of our new subject, Sub-Zero 2. As you can see, very straightforward but precise gameplay. Run when there's no enemy on the ground, and swing his sword when there is. Let's look at a second video. Very similar. So now, let's look at our best static deep neural network agent. So it's running, but is not neutralizing the first enemy in the same way, and it stops in front of the second. Now, let's look at agents equipped with networks of dynamic complexity. Looks much more similar to Sub-Zero 2. Let's look at a second one. Same thing. Alright, dynamic networks seem to even be an upgrade. Looks like we're on the right track. Alright, so what's next for this project? First of all, we learned a lot from designing these dynamic networks. We've noticed some issues with the current version and are looking to iterate onto a version 2.0. Next, as you might have seen earlier, we're starting to really be able to leverage lots of computation. Our next step is to run these algorithms on Summit, one of the most powerful supercomputers in the world. And finally, we'd like to begin to start integrating brain dynamics into the loop. Alright, that's it for me. I'd like to thank the whole NeuroMod team for being awesome, and La Fondation Courtois for giving us the opportunity to work on this amazing project. And finally, thanks to all of you for listening. Bye bye!